Okay, in this problem, we're going to have this is problem 15.40, and in this problem we have this collar B, and this collar B is constrained to move along this rod in the vertical direction. So this is just some rod that it's over. So here's B, and it's connected to this point A with this link. So this right here is going to be point A. And we know that the angle A makes with the horizontal is 25 degrees. We're told that this angle B makes right here is going to be 50 degrees. And we're told B moves upward with a constant velocity of 1.5 meters per second. We're also given the distance of A to B. And this distance right here is 1.2 meters. So we're asked to figure out what this velocity of A is and what the angular velocity of this rod AB is. So if we use our constant velocity, our relative velocity equation, we have the velocity of A is equal to the velocity of B plus omega AB crossed with the position vector of A with respect to B. Okay, so the next thing I like to do is draw a kinematic diagram. And in this diagram, I'm going to put all my vectors, so my velocities and my position vector and angular velocities. So at point B, we know that our velocity is coming up at 1.5 meters per second. And we're not given anything about this point A, so we're going to assume it has a positive velocity in both the y and the x direction. So it's going to have a velocity of A times the sine of 25 and a velocity of A times the cosine of 25. Our angular velocity we're not given anything about, so we're going to assume it has a positive angular velocity. And our position vector, it's this position vector r of A with respect to B. Since B is up here, it's where we start and we go to A. So we start at B, we go to A, and this line right here becomes our position vector of A with respect to B. And we know this right here is 50 degrees. So this angle right here is 40 degrees. And I just like to keep my cosines with my eyes if I can help it. So it's fine if you do this the other way, but I know that this distance right here is going to be 1.2 times the cosine of 40 I, and this is a negative, and a negative 1.2 times the sine of 40 j. So what this distance is right here is I'm coming at this distance. This is my 1.2 times the cosine of 40, and I'm coming down this distance right here, and this is my 1.2 times the sine of 40. Okay, so I have all my variables, and again, I like to, I guess, do it the long way, and I write out everything I have. So my velocity of A is VA times the cosine of 25I plus VA times the sine of 25J. My velocity of B is equal to 1.5J because it's going in the vertical direction. My omega AB is equal to, we're going to assume it's positive, so omega ABK. And my position vector, r of A with respect to B, is equal to minus 1.2 times the cosine of 40I minus 1.2 times the sine of 40j. So let's plug everything into this equation. And when we do that, we get VA times the cosine of 25I plus VA times the sine of 25j is equal to, I'm going to run out of room, so I'll just extend it down to this next line right here. This VB, which is 1.5j plus omega ABK, which is crossed with a minus 1.2 times the cosine of 40i minus 1.2 times the sine of 40j. Let's take a look at this cross product right here. This cross product, if we simplify it out, we're going to get a minus 1.2 times the cosine of 40 times omega AB of a k cross I, which is just j, and we're going to have a minus 1.2 times the sine of 40 omega AB of a k cross a j, which is a negative I, and I will distribute that negative sign. So this is what that equation becomes, and I'm just going to simplify this, multiply this out a little bit. So when I do this, I'm going to lose some of that resolution that the answer in the back of the book has, but it comes out to the same answer if you don't multiply this all through. So I have a minus 0.919 omega AB j plus a 0.7713 omega AB I. So this is that cross product right here. Now I want to take my I and j components, and with my I components I'm going to have a VA times the cosine of 25, which is equal to, this is a j component. So this is this velocity equation. It's just broken up into two lines. So it's going to be equal to a 0.7713, and I'll just cross this out a little bit, just so you see the equation I'm working with, omega AB. We can solve this equation for omega, the angular velocity, and we have the angular velocity of B is equal to VA times the cosine of 25 over this 0.7713, and if we perform this calculation, we get it's equal to 1.17 VA. Now if we look at our j components, we're going to have VA times the sine of 25 is equal to this 1.5 right here, minus a 0.19 omega AB. We have this expression right here for omega AB, so we have VA times the sine of 25 is equal to 1.5 minus 0.919 times 1.17 VA. And this turns out to be 1.5, so VA sine of 25 is equal to 1.5 minus 1.07 VA. And when we add this VA to this side of the equation, we're going to be able to solve for VA, and we're going to have VA is equal to 1 meter per second. And this is close to what the book has. The book has, I think, 0.998 meters per second, and if you had done all this calculation out without multiplying the cosine of 40 right here, you'd get the answer in the back of the book. So now we can plug this VA back into right up here. So we get omega AB is equal to the cosine of 25 over 0.7713, and omega AB is going to be equal to 1.176 radians per second in this direction.